So hopefully your break is going well. So this first video is going to be about section 7, which is titled Indeterminate Forms and the LHopitals Rule. So we're actually going to take kind of a step backward, and we're going to talk about limits again. And the reason is because section 8.8 has to use limits for a particular kind of integral. Now you'll notice that we skipped section 8.6, and 8.6 had more applicability when we didn't have computers to do complex integrals, or we didn't have numerical methods that were easily available. They're basically using tables of integrals, and I'll talk about that when we get back, but we're not going to go into a lot of detail on that. So the whole concept here is, back in chapter 1, we had certain functions. When we took the limit, we initially got an indeterminate result. So here's our function, and if I said, what is the limit of this function as x approaches 4, the first thing you do is you just plug it in there and see what you get. And what you'll see is I get 16 minus 12, which is 4, minus another 4, which is 0, and 4 minus 4. So this is indeterminate. And what we did in the first chapter is we factored the numerator. So we'll get x minus 4 and x plus 1 divided by x minus 4. And we cancel those out. That was why we were getting the indeterminate result. And then you plug in x equals 4 now, and you would get 5. So the limit of this function as x approaches 4 is 5, even though the original value is indeterminate. Now the problem is that there are other rational results where you have some function divided by another function where you get an indeterminate result, but you can't use one of the techniques that we've already talked about. Let me just pause this for a second. I'll close my email. So LHopitals rule is this: if you have a limit of the ratio of two functions as x approaches c, and you get an indeterminate result, then what you can do is you can take the derivative of the function in the numerator and divide by the derivative of the function in the denominator, and you take the ratio of the limit as x approaches c for the ratio of the derivatives instead of the original functions, and that gives you the same result. So let's just look at the previous one, which we know the answer is 5. So in this case, f of x would be the term in the numerator, and g of x would be the denominator. And then if we take the derivative, just use the power rule, so we get 2x minus 3, and here we get just 1. So that says that the limit of the original function as x approaches 4 is the same as the limit as x approaches 4 of the ratio of the first derivatives. And this is not going to be indeterminate, so I just plug the number in. So I'll have 2 times 4 minus 3 divided by 1, which is 8 minus 3, which is 5. So you see I get the same answer. Here I used the canceling out technique. Here I used what's called LHopital. So it's not LHopitals, it's LHopital. It's French guy. Okay, so we just did that one. And back in chapter 1, we had this indeterminate form, 0 divided by 0, but there are not a lot of other indeterminate forms. You can have infinity over infinity. You can have infinity minus infinity. You can have 0 raised to the 0 power. You can have 0 times infinity. You can have 1 to the infinite power. So these are other examples of indeterminate forms that can be addressed using L'Hopital's rule. So we'll look through some examples. So again, this one we probably could solve using rationalization, but we're going to use L'Hopital's rule. Again, first thing you need to do is plug it in there and see, does it give you 0? So you get square root of 4 minus 0. So square root of 4 minus 2 over 0. And square root of 4 is 2. 2 minus 2 is 0. So it's indeterminate in the classical fashion. So what we do is we call the numerator, and I'm going to rewrite it as a fractional exponent while I'm thinking about it. So you get that, and you get g of x, which is x. So g prime of x, that's the easy one, is 1. And for this, you would use the chain rule. So you would say f of u is u to the 1/2 minus 2. U of x is equal to 4 minus x squared. F prime of u is going to be 1/2 u to the minus 1/2 power. And u prime of x is equal to negative 2x. We don't do the dx here. The dx is u prime of x is du dx, so we don't have the dx part. Okay, so we plug that back in. F prime of x is f prime of u times u prime of x. 2's cancel out. Plug u back in. So you end up with negative x. Okay, so there's a negative sign, there's x, and then you'll have the square root of, so this goes to the denominator, becomes a square root, and you get 4 minus x squared. So that's f prime of x. So what we do is we take the limit as x goes to 0 of negative x divided by the square root of 4 minus x squared divided by 1. G prime of x is 1. This is f prime of x. So now if we plug in 0, you'll notice we do not get an indeterminate result. We get negative 0 divided by the square root of 4 minus 0 squared divided by 1. So you get negative 0 divided by 2 divided by 1, which is going to be 0 ultimately. So the limit is 0. Now how about the squeeze theorem? So we derived the squeeze theorem. If you remember, we looked at a unit circle, and we looked at the area associated with the sector and with a triangle, 2 different triangles, and we proved that. But and the answer was 1, correct? So using the L'Hopital's rule, f of x equals the sine of x, g of x equals x. So f prime of x equals the cosine of x, and g prime of x equals 1. So the original limit of the original functions could be replaced with the ratio of the derivatives. And now if I plug 0 in, I'll get cosine of 0 divided by 1. Cosine of 0 is 1, so you get 1, which we knew that was the answer from the first chapter. So it was a lot easier to prove the squeeze theorem using L'Hopital's rule. Okay. Again, I didn't do it in the previous one, but we had the sine of 0 divided by 0. Sine of 0 is 0, so it is indeterminate. And the same here, you get the sine of 0 divided by the sine of 0. So it will end up being indeterminate, which means, well, up to this point, we've done problems that we know how to do previously. We've known, we used the canceling out technique here. We could have used rationalization here. We could have used the squeeze theorem there, but this one is not one that we know how to do. So again, you say f of x is the numerator. And g of x is the denominator. So when you take the derivative, the chain rule, remember you take the coefficient. When you're taking the derivative, you multiply by the coefficient. The derivative of the sine is the cosine. Same with the other one. You get 3 cosine of 3x. And so the original limit ends up becoming the limit of the ratio of the derivatives. And because now we have the cosine of 0 is not 0. So you get 2 times the cosine of 0 divided by 3 times the cosine of 0. But the cosine of 0 is 1. So you get 2 times 1 divided by 3 times 1, which is 2/3. Now I want to look at this one just graphically to see show you what's happening. So let me minimize this and open up my graphing program. So I'm going to do the sine of 2x divided by the sine of 3x. And I say graph. So if you zoom in at x equals 0, you can see that the limit is 2/3. But that's actually not what I wanted to show you. I wanted to do the sine of 2x and the sine of 3x and see how they compare. So what you can see is that, as we zoom in, when you get close to 0, they just look like linear functions. And so no matter how far we zoom in, you're going to get the ratio of these two functions is going to remain the same. So that's kind of the concept here, is that away from 0, the functions diverge quite a bit, but when they approach 0, they become very linear looking. And so the numerator, which is the denominator, just become a constant ratio as you come down. Okay, so I just did that. So now we have another thing. It's the ratio of two different kinds of functions. So again, what we do is we call the function in the numerator f of x, and the function in the denominator g of x. So if we take the derivative, we end up with 3x squared, and the derivative of the numerator is going to be 1/2 e to the x over 2. We're using the chain rule. U of x would be x over 2. The derivative of x divided by 2 is 1/2. So that's where the 1/2 comes from. That's u prime of x. And the derivative of e to the u is e to the u, so that doesn't change. So it's kind of like with trig functions. If you have a coefficient inside the exponent, just the coefficient times x, then it's usually pretty easy to to do the derivative without having to write it out fully. Now, I initially, I had, if I had 0, or actually infinity, so infinity cubed divided by e to the infinity divided by 2, well, that's going to be infinity divided by infinity, which is indeterminate. It's that different kind of indeterminacy. Now, if we look at the derivatives here, you can see where I have the same dilemma. If I stick infinity in here, it's still going to be infinity. If I stick infinity in there, it's still going to be infinity. But what we can do is we can continue to take derivatives until we get to somewhere where we actually can do something. So if we take the second derivative of x, f of x, we'll get 6x. And the second derivative of the next one, same thing happens. When we take the derivative again, we'll get another factor of 2 in there. So it'll be 1/4 e to the x over 2. And then the third derivative is just 6. And the third derivative is going to be 1/8 e to the x over 2. Again, at this point, if we took the ratio of these two, we'd still have infinity over infinity. It's not until we get to this part where we don't, one of the terms is not infinity, so it's not indeterminate anymore. So that's what we're going to do. We're going to look at the limit as x goes to infinity of 6, so the f triple prime of x divided by 1/8 e to the x over 2. Well, in this case, you're going to get 6. If you plug in infinity, you're going to get 6 over infinity. It's no longer indeterminate because we don't have infinity in both the numerator and the denominator, but this is a constant. This is infinity. The answer is 0. So that's, it's entirely acceptable response, 0. Now let's look at a graph of those two things again. So if you have x cubed and you have e to the x divided by 2, if we plot those, you see this happening. And initially, the x cubed, which is the red curve, is below. And you can see how this one's rising more rapidly. So you'd think that actually the numerator, which is x cubed, would increase more quickly than the denominator. But if we zoom out enough, actually, that's going to stay the same, right? Oh, no, it's not. Yeah, I should have gone back here. So there's this point here. So let's go back to here. Anyway, it looks like x cubed's getting faster. And so ultimately you expect that one to be greater than that, but that's not what happens. So let's go back. So I'm just going to zoom out in this direction. And finally, there we go. I knew it was going to happen sometime. They cross over. So once you get to numbers larger than about 17, the exponential function starts to grow more rapidly than the x cubed. So this is getting a lot bigger than, more quickly than that. And so this ratio becomes larger and larger and larger. Okay. Now we've also done this problem before. This was section 3.5, and we'd say we take the limit, we take the ratio of the coefficients in front of the highest order term to do that. Now if you plug infinity in there, you'll get infinity over infinity, but we had that rule about if you have the same order in the numerator and the denominator, it's a ratio of those. But let's use L'Hopital's rule. And I'm going to put g of x down here. So f prime of x is 6x minus 2. G prime of x is 4x. So again, if I took the ratio of this to this, I'd still have infinity over infinity, so you have to do it twice. So the second derivative is going to be 6, and the second derivative here is going to be 4. So I just take the limit as x goes to infinity of 6 divided by 4, and because x is not in either of those two terms, it's going to be 6/4, which is 3/2, which is the same as taking the ratio of the leading coefficients. Okay, let's try this one. Again, plug infinity in, you're going to have the natural log of infinity, which is infinity divided by infinity squared. So that doesn't work. That just gives you infinity over infinity. So it's indeterminate. So f of x is the natural log of x. G of x equals x squared. F prime of x equals 1 over x. G prime of x equals 2x. So I can replace that of I get 1 over x divided by 2x, and if you plug in infinity, you'll get what you'll get is 1 over infinity divided by 2 times infinity. 1 over infinity is 0, and 2 times infinity is infinity, so you get 0. Now, if you simplified it, so if you took that, what you would do is you would take 1 over x times, you take the reciprocal of that, which would be 1 over 2x, and so you get the limit as x goes to infinity of 1 over 2x squared, which is also 0. And what you see is that this thing grows much more rapidly than that. And so this fraction gets ever smaller. So all of these indeterminate forms involve single fractions. What happens if I have one of the other indeterminate forms, like 0 times infinity or 0 to the infinite power? Well, what you can do is you can take this product and make it into a quotient by taking the reciprocal of one of these terms. And then it becomes either infinity or 0 over 0. So here's an example. So what I want to do is take the limit as x goes to 0. And the reason there's this plus thing here is because the cotangent of 0 does not exist. Actually, that's not true. Cotangent of 0 is... yeah, this doesn't exist because the tangent of 0 is 0, so the cotangent would be 1 over 0, which would be infinite. So at 0, you've got a vertical asymptote. And obviously, because if you see I put in 0 into the cotangent, I get infinity. And put in 0 for x, I get 0. 0 cubed is 0. So what I do is I would make it into a ratio. That's when L'Hopital's rule works. So if I did x cubed divided by 1 over the cotangent of x, but the 1 over the cotangent is the tangent. So now my original equation is rewritten as a ratio. Here I had 0 times infinity. In this case, I'll have 0 divided by 0. So it'll be a different kind of indeterminacy. So at that point, you can say, okay, we'll just need to say f of x equals x cubed, and g of x equals the tangent of x. So I take the first derivative, f prime of x equals 3x squared, g prime of x equals the secant squared of x. Now you might think, oh, do I have to take the derivative again? Well, only if you plug these in, you would get an indeterminate result. But in this case, what you'll get, so if we put 3x squared over secant squared of x, if you take 3 times 0, remember on the one side of the limit, you can just plug the number in, and if it works, great. The only time you have to worry about is if you got infinity. So we plug 0 in, so we get 3 times 0 squared divided by the secant of 0, quantity squared. Well, the secant of 0 is 1, and 0 squared is 0. So you'll get that. So the answer is 0. So let's actually look at this. Graph these things. So where's my graphing program? Must have closed it. Oh, there it is. So we'll do x cubed, and I'm going to do the tangent of x. And I'm going to have to zoom in here. Okay. Did I do both of them? No, I need to put a colon in there, semicolon. Okay, so there we go. So the red curve is x cubed, and the blue curve is the tangent. So if we zoom in on 0, what you'll see is that the red curve approaches 0 much more quickly than the blue curve. So the numerator is going to be much smaller than the denominator. And as you approach 0, that difference becomes even larger. And so that's why the ratio is 0. Now, you might have something like this, where you have the limit as x goes to infinity of x to the 1 over x power. So if I plug infinity, you'll have infinity to the 1 over infinity. Well, 1 over infinity is 0. So I get infinity to the 0 power, which is another indeterminate result. And you can't immediately convert it into a fraction. So it's not a LHopitals Rule problem. So is there any way I can convert this into a fraction or into a product that I can convert into a fraction? Well, this is where you have to use logarithmic differentiation. So what you do is you take the logarithm of both sides, including the limit. So you can take the limit inside. So you'd have the limit of x to the 1 over x power. So we're taking the limit as x goes to infinity, and using the properties of logarithms, we can take the exponent and multiply it by that. Now what we do is we can then convert this into a ratio. Okay, so we're going to take the limit as x goes to infinity, excuse me, and So let's see what we got here. So you get the natural log of x over x. Okay, so you'll see you get infinity over infinity. So it is indeterminate now. So we have gotten a different indeterminacy, but it's 0 over 0. So what you do is you take the derivative with respect to x of the natural log of y, and then you take the derivative with respect to x of the ratio. That's what we've been doing using LHopitals rule. So let's see what happens there. So the derivative of the natural log is just 1 over x. So that's so you get 1 over x divided by 1. So now it's not indeterminate anymore, but you just get 1 over infinity, which is 0. Okay. Now on the right hand side you have the derivative of the natural log of y, which is 1 over y times y prime. That's implicit differentiation. So so we get y prime is equal to, what are we doing here? Yeah, I'm trying to remember whether I need to do that or not. It's kind of a combination of stuff, so because I think what I remember is what you do is you don't really do that. What you do is you take the result and you take so this y is really just this limit thing. So what you do, so it's not really, and then what you do is, since this is natural log of y, to solve for y again, you take e to the natural log of y, and you take e to the 0, which is 1. So the original limit was 1. So that number should approach 1. So let's just check it out. This is one that I won't put on the test, but it does just give you an idea. Okay, so what I want is to plot x to the 1 over x power. So we graph that, and this is as x goes to infinity. So let's go to standard, and then we'll just zoom out in the x direction. And you can see that when you zoom out in this direction. So if I keep going, you can see that we're approaching 1. So that is the right answer. So this y is not really a coordinate, that's the limit. So you take the natural log of both sides so that you can break this up into a ratio using LHopitals rule to take the derivative, but you're not, what we're doing is going from here to here is using LHopitals rule. And then once you get to the end, you have to solve for what the limit was, which is y. And there you go. So that's the homework for section 7. So you get a little short version. So we're going to stop, and we'll go to another recording for section 8. See, in section 8, there's just a few limited cases where we use LHopitals rule, but we still need to have it.